If you're alive and watching this video, chances are at some point in your life you've used a copy machine. Well, I'm about to blow your mind with the latest innovation in copy machines. No, it won't save you money on toner or jam less. Imagine a copy machine with a really expensive GPU that does lots of math and spits out exactly what any other copy machine would. It's called an autoencoder, and it's the bee's knees in deep learning. This is Colin Scow, and welcome to another tutorial in the School of AI's Data Lit series. So what does an autoencoder do exactly? It takes in an input, crunches it through a deep neural network, and if trained properly, spits out the exact same data it was fed. So why is that so special? Well, I'm glad you asked. The secret is in the bottleneck. See, we're not just passing data straight through a network. We're choking it off in the middle, which forces the network to generalize a low-dimensional representation of the data through the encoder, then regenerate the original data through a decoder. So obviously using a deep neural network to merely copy the input is a tremendous waste of computing power. In most cases, we don't care about the output, we care about the dimensionality reduction and compression which happens in the bottleneck. Say we've got a data set with images of different kinds of flowers. For each image, it's got to figure out a simplified way to encode what's unique about that flower in the hidden nodes in order to instruct the decoder how to redraw it. We'll see the neural network figure things out like color, shape of petals, and type of texture. So what useful things can we do with autoencoders? Probably the simplest practical use case is data denoising. We add random noise to the training input, but then calculate the loss against the original input with no noise. Noisy images go in and clean images come out. A variation of this is learning how to fill in missing data. For example, you can add random blanks to your training images and, as before, use the original images as the expected output. The result is a neural network which has learned to intelligently guess missing pixels. This is great for removing objects and watermarks from photos. Remember before how I said the most valuable part of an autoencoder is a bottleneck? Well, here's one of the coolest use cases. What happens if we train an autoencoder on a few thousand images of Nicolas Cage, train a separate autoencoder on a few thousand images of Donald Trump, and then connect the Trump encoder to the Cage decoder? The result is one of the most controversial breakthroughs in deep learning: deep fakes, or the face swap.
Thank you very much, my fellow Americans. I am very proud to announce today that we have reached a deal to end the shutdown and reopen the federal government.
This meme has become so pervasive, it's been announced that Nicolas Cage is going to be the running mate for 2020. Sorry, Mike Pence, you've been caged. When you train an autoencoder on one face, the decoder learns all the details of the face and the bottleneck stores intricacies about angle, facial expression, etc. So by swapping decoders, we can now translate one face to another with things like expression, lighting, and angle intact. There's software which will automatically detect the faces frame by frame in videos and mask them out and replace the original face with the one output by the neural network. The code to do all this gets a bit more complex than I want to go in a beginner level tutorial, but I'll leave a link in the description if you want to learn more. For this week's coding tutorial, we're going to focus on one of the most practical and in-demand applications of autoencoders, building a recommendation engine for movies. The task is quite simple. We're going to use a data set called Movie Lens, which includes 1 million ratings of 4,000 movies by 6,000 users. We've got a table of data. Each row is a user. Each column represents a movie, and the cells, the user's rating for that movie from 1 to 5, or 0 if the user hasn't rated the movie. The data is quite sparse, which means that most ratings are 0. We're going to create an autoencoder where we input all the movies a user has rated so far and get back a prediction for the rest. How does it work? As with standard autoencoders, the target data is exactly the same as the input data. However, as each user has only rated a small portion of a large catalog of movies, we only calculate loss based on the movies the user has actually rated. In other words, during training, we completely ignore the predictions that the network makes on unrated movies. We do this by masking them out during the loss calculation. Once the network is trained, we can then feed a small list of movies the user has rated into the network and get back predicted ratings for the rest of the catalog. Hot tamales, let's dive into the code. We've got 3 input files which are each in a CSV format separated by double colons. The movies file contains an integer ID, the title, and a list of genres for each row. The users file contains an integer ID and some demographic information. The ratings file contains a user ID, a movie ID, a rating, and a timestamp in each row. We calculate the total number of users and movies by finding the maximum ID value for each and adding 1 since they are 0-based. Now we build a NumPy matrix with number of users as rows and the number of movies as columns. We loop through each row in the ratings table and insert the rating in the proper cell of the user ratings table. The next step is to split the data into training and test sets. We'll use an 80-20 split. Next, we detect if a GPU is available and convert the training and test sets into PyTorch tensors. By the way, make sure GPU is turned on inside your Kaggle notebook. You can find this in settings on the right side of the page. The next part is the training hyperparameters. These are values which you can experiment with and tweak in order to improve the accuracy and performance of your model. Hidden outer size is the number of neurons in the outer hidden layer. Hidden inner size is the number of neurons in the inner hidden layer or bottleneck. Num epochs is the total number of passes we'll make over the training data. Learning rate determines how much the weights change at each step of backpropagation. Too high and you'll miss a sweet spot. Too low and training will take forever. Weight decay or regularization is a technique which helps make training more stable and reduce overfitting. Do a Google search for weight regularization if you want to learn more. Now we build the actual network. It consists of input, 3 hidden layers, and the output. To create each layer, we need to specify the input size and the output size. Each layer except the last passes through a sigmoid activation function. Next, we have a slightly modified mean squared error loss function. Instead of averaging by the total number of movies, we're going to divide by the number of actual rated movies, ignoring those with zeros. Then we create an instance of the deep autoencoder network and assign it to the selected device. We also initialize the Atom optimizer. Now we reach the meat of the code, the training loop. We grab a batch of rows from the dataset. We make a copy of the input into a variable called target, then send both to the GPU. We don't need to calculate gradients on the target, so we'll disable that. We calculate the number of rated movies by each user over the entire batch where there is a value greater than 0. We make sure there is at least 1 rating in the batch before proceeding. We pass the input into the deep autoencoder to get a prediction. Since we don't care about unrated movies, we're going to zero out all the predictions for unrated movies so they don't pollute the loss function. Next, we calculate the loss. In order to print it out, we'll need to move it to the CPU and then export it as NumPy. We're going to track the total loss over the entire epoch. Finally, we backpropagate the gradients from the loss function through the network and run the optimizer to update the weights. At the end of each epoch, we print the total loss divided by the total number of steps taken during that epoch. Last, but not least, it's time to evaluate our model to see how well it predicts data it never saw during training. This is done exactly as we did in our training loop, but without backpropagation. And it looks like we have a solid model. All right, thanks for tuning in. This is Colin Scow. Make sure you like and hit subscribe if you found this useful. I'll be back next week with another deep learning tutorial. Meanwhile, keep the data lit.